Okay, thanks to organizer. It's my 25th time in Russia, but the first time in Moscow, so in this important institute. So it's really a pleasure for me. As Sergei said, it's a joint work with Paolo Cristofori from the University of Modena Reggio Emilia, and Eugeni Fuminik and Vladimir Tarkayev from Chelyabinsk State University. My university is the University of Bologna. Okay, the combinatorial object involved in this talk are a four-colored graph. What is a four-colored graph? It's a very simple object. Four-colored graph. A four-colored graph is a connected, finite, multigraph, so multiple edges are allowed, multigraph, without loops, no loops, because of coloration, regular of valence 4. So each vertex of the graph has exactly valence 4. Colored, properly colored. Properly means on the edges. Properly means that two adjacent edges have different colors. It's clear from the slides. On the edges with exactly 4 colors. Which we will call 0, 1, 2, 3 usually. Okay. So this is the combinatorial object. From this object it's possible to obtain 3 manifolds, and okay, so locally the object looks like that. Any vertices has valence 4, any edges are different color, 0, 1, 2, 3. There are the simplest example of four-colored graph are here. With two vertices, there is only one. With 4 vertices, there are these 2, and then another one. These 2 are bipartite, so you can divide the vertices in 2 classes, and each vertex of one class is connected to vertices of the other classes. Not all 4 regular graph can be 4-colored. It's easy to see that a 4-colored graph should be order even. For example, this is order 3. There is no way to color properly with 4 colors. But also a graph with even number of vertices can be, for regular of course, cannot be 4-colored. For example, this graph is 4 regular, but there is no way to 4-color it. From this type of object, or this class of object, there is a construction which gives 3 manifolds. Exactly this, our job is the second step of a very old story. The very old story comes from the 70s, 80s. 2 groups of researchers. In the 70s, Pezzana group in Modena, and in the 80s, Lin's group in Recife, in Brazil, introduced dual construction. The construction is dual. We will follow the Linz construction, but the other is dual, so give the same result. To construct closed manifold from four-colored graph belonging to a special class. Linz called them gems. In some sense, four-colored graph is a gem if a combinatorial relation is satisfied. The combinatorial relation means that Euler characteristic of the resulting complex is zero, so it gives a closed trimanifold. So they give independent with dual construction a way to construct closed trimanifold from particular four-colored graphs called gems. This combinatorial tool was very convenient in order to construct catalog of trimanifold by increasing number of vertices. Of course, if you fix a number of vertices, there are only finitely many four-colored graphs of that order, and they give a big catalogation and classification of closed trimanifold representable by gems of order less than or equal, I don't remember, 32 or 34 vertices, the last classification. It was performed by Linz and by Modena people separately, but more or less the same result they achieved. So it's very useful combinatorial tool to represent it trimanifold. Of course, there are a lot of connections with other representation as surgery, dense surgery, and branched coverings, and especially agar splittings, etc., etc. Everything is, a lot of work was done, but only in the closed case. Only in the closed case. What about non-closed case? What about trimanifold with boundary? So people in Modena tried to represent manifold, trimanifold with boundary using a slightly different combinatorial tool. They use almost four-colored graph. Almost means that the vertices of the graph can have valence 4 and valence 3. So they go out from the class of colored graph and give this such a representation for non-closed boundary. But this representation was not good as the previous one, because some vertices of valence 4, some vertices of valence 3, it was difficult to obtain a result algorithmically so nice as in the closed case. So very few papers are devoted to this construction, but a few years ago, following also a suggestion of Sergei in his book, we understand that it's not necessary to go out from the class of four-colored graph in order to represent compact trimanifold with boundary. Just take the other graph in the class of four-colored graph, which are not gem. Following the construction of Linz, we obtain all compact trimanifold with boundary except the one with boundary which are spherical. But if the boundary is spherical, topologically it's nothing, because you just count how many spherical boundary you have and fill with ball. And so our construction, and I will show, give a representation via four-colored graph, so no, almost, so only object of this type, for all compact three-manifold with boundary which is not spherical. All type of boundary components are allowed except spherical ones, which are not interesting topologically. Okay, the important thing in four-colored theory, graph theory, are residues. What is a residue? Is just a subgraph spanned by some of the four-colored fixed. For example, zero residue, there are no colors, so no edges are vertices, but not very interesting. One residue, you choose a color, so it's edges of a certain color, so one residues are edges. But the interesting residues are two residues and three residues. What is a two residue? You fix two colors and consider the subgraph spanned by the edges of these two colors. So, of course, they are bicolored cycle of even order. And what is a three residues? Three residues is a subgraph of a four-color graph spanned by three fixed colors. Of course, connected components. Any connected components of the subgraph spanned by three fixed color is a three residue. And for any three residues, you can associate a color, which is the missing one. For example, this is a three residues. The missing color is zero, so we can associate to these three residues the color zero. We will see that three residues are associated to boundary components of the manifold. So in our construction, the boundary components have some color. Okay, the construction will follow exactly the construction of Sosthenes lines. Take the graph, the four-color graph, as one-dimensional CW complex is one skeleton of the future manifold. Attach a disk to any two residues. So for any bicolored cycle, you attach a disk. After attaching this disk to any two residues, you obtain a two-dimensional complex. This two-dimensional complex is a spatial complex, and it will be a spatial spine of the future manifold up to some puncture, possibly. Okay, after this two-dimensional complex, we should add some three-dimensional objects. Let's think to three residues. If you consider a three residues, which is disk attached, so since for any bicolored cycle you attach a disk, any edges as exactly in the manifold three disks attached in the manifold. But in any three residues there are only two disks attached to any edges, so any three residues together with the attaching disk is a surface, is a closed surface. We call the three residues ordinary if the surface is S2, sphere. We call the three residues singular if the surface associated to this residue is not a sphere. It can be any surface of any genus, orientable or non-orientable. So, what is the operation in order to obtain the three manifold? Attach a three ball to any three residues which is ordinary, which is S2, sorry. So for any S2 in the in the two polyhedra, special polyhedra, you attach a triball, and if the residue is singular, so it's not S2, you just thicken it. You attach S times I along S times 0. You just give a three-dimensional dimension to that surface. So at the end of the story, we obtain a three-dimensional compact manifold with possibly empty boundary, but the boundary has no spherical components because we fill all sphere by balls. Of course, boundary components correspond to singular tree residues. Yes. So at the end of this construction, we obtain a closed tree manifold if all tree residues are ordinary. So all tree residues are sphere. If there is at least one residue which is not ordinary, which is not a two-pole, we obtain a boundary component. For any residues which is not ordinary, we obtain boundary component. And recall that we can associate a color to this boundary component, because the boundary component corresponds to a tree residue which is not a sphere, and any tree residues has a missing color, so we can associate this missing color to the residue and to the component of the boundary associated. So there is a theorem proved by me and Paola Cristofori. Any compact possibly closed tree manifold with non-spherical boundary components admits representation via four-colored graph. This is exactly the construction of lines, but lines only take gems. Gems are exactly four-colored graph where all tree residues are ordinary, are S2, so from this construction you get closed tree manifold. This is generalization giving all compact tree manifold without spherical boundary components.
So gamma is the four-colored graph.
Sorry?
Gamma is the four-colored graph.
Gamma is four-colored graph, yeah. Yes, yes. Sorry, I didn't say.
So this, you mean any compact three manifold can achieve as any gamma?
Yes, 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 yes. Not uniquely, unfortunately. There is no unique representation. That map is subjective but not objective. For any tree manifold, you can have infinitely many different graphs which give the same tree manifold, but this is usually in any representation of tree manifold. Yes? Yeah, I'm just speaking about this. Since there are infinitely many different graphs giving the same tree manifold, it's very important to obtain exactly what you suggest, a list of moves. Okay, there are some examples. For example, this is the real projective plane times I. This is the solid plane battle. Both of them are non-orientable, and you can see that the graphs are not bipartite in these two cases. And the other two examples are the solid torus, H1, underbody of genus 1, and S1 times S1 times I. Both of these two are orientable. In fact, there is a bipartition of the vertices into class where any edge goes from a vertex of one class to a vertex of the other class, the vertex will start. Because there is an easy result, which was, of course, also true for closed case. A manifold represented by graph gamma is orientable if and only if the graph is bipartite. Okay, moves. So we need some moves to connect different graphs giving the same manifold. These moves are well established in the closed case, and it's proven that the move in the closed case are enough to connect different graphs giving the same manifold, but in the non-closed case it's not true. We will mention this. Okay, moves are called dipole moves. There are some local configuration in this. For example, this is the 3 dipole moves. You have 2 vertices connected by 3 edges, and you just remove this dipole and glue the 2 pendant 3 edges here, 1 edge here. You go in one way and also in the other way. This is called a 3 dipole. There are also, in the case of 2 dipole, there are 2 edges, and there is a condition. They are not completely local, because in order to have a dipole and to have an admissible dipole, you need that the bicolored circle with the other 2 colors of the 2 vertices are disjoint. So this circle is disjoint by this circle. So in this case, the dipole is proper or admissible, and you can perform the move just removing the dipole and attach the edges with the same color.
What's the color for the upper?
Is 0.
Color 0?
Colors, yeah, 0, 1, 2, 3.
And then for the next, also 0.
Yes, this is 0, yeah. Yes, because in the previous slide I put some snake instead of 0, but here is 0. Color 0, color 1, color 2, color 3. Thank you. And what about one dipole? There is only one arc between the 2 vertices, and the 3 dipoles, 3 residues containing the other color edges of the 2 vertices are disjoint. So these 3 residues is disjoint from these 2 residues. And you can perform the dipole moves. In the closed case, all 3 dipole moves are admissible. You can do in one way and the other without any problem if the disjoint condition is satisfied. And Casali proved that these 3 moves are enough to connect all graphs representing the same closed manifold. In the non-closed case, it's not true. First of all, in order to perform this move, the tier 1, the 1 dipole moves, you should check that at least one of these 2 residues, 3 residues, there are 2 involved, this and this, at least one is a sphere. Otherwise, if both are not sphere, they correspond to different boundary components, and if you perform the move, the 2 boundaries attach and you destroy the topology of the manifold. So in the non-closed case, this moves is not always possible. It's possible only if at least one of the 3 residues is a sphere. And unfortunately, it's easy to prove that they are not enough. Why they are not enough? To connect different graphs of the same 3 manifold with boundary. Because moves does not change the color of the boundary. So the color of the boundary is unaltered by moves. It's easy to construct 2 graphs of the same 3 manifold with 2 boundary components, one with the same color of the 2 boundaries, and another graph with different color. So there is no way to pass from a graph with all boundaries of the same color with a graph of the same manifold with boundary of different color. Is under we are studying if this is enough in the subcase where the boundary is connected. So if the boundary is connected, maybe this is enough, but we don't know. And also, if you consider a graph with the same color of all boundaries, is a restriction which is not very suitable, because if we ask that all boundary components are the same color, the number of vertices becomes bigger. So it's not very convenient, but anyway. So these are moves. These are moves connected almost locally, graph which represent the same manifold. If you perform moves, the topological type does not change if the move is admissible. So when we produce catalog of graph representing compact tree manifold with some number of vertices, we can avoid a graph which have this type of configuration, because we can perform moves, and from the left to the right you remove vertices. And so when we construct catalog of graph, we can discard graph which contains 3 dipole, 2 dipole, or 1 proper dipole. Okay, then the first computational result are the following. With 2 vertices, there are no graph representing closed tree manifold, because, okay, this represents S3, so is not is not our case. We only study case with boundary. And so with 2 there is nothing. With 4 there is only 1, is non-bipartite, is exactly this one, which represents the projective plane times I, because the other 2 with 4 vertices represent S3. So this represents the 3, this represents the 3, no boundary. So the only case is this one with 4 vertices. With 6 vertices, there are these 3 cases. So the solid plane battle, no, maybe there are more, but solid plane battle, solid torus times I, but the real classification is with 6. We have 2 bipartite, the solid torus and the torus times I, and 6 non-bipartite, including the solid plane battle. And with 8, there are 4 bipartite and 90 non-bipartite. And as you can see, the number of graphs, these are non-isomorphic graphs, of course, without dipole. The number grows very rapidly, especially in the non-bipartite case, which correspond to non-orientable tree manifold. Okay, so by hand, only by hand, me and Paola tried to classify the case up to 8 vertices in bipartite case, and the case up to 6 vertices in the non-bipartite case. This result was obtained 2 years ago and published last year in RAXAM. RAXAM is acronym of a journal in Spain, Royal something, I don't know. Okay. Of the 7 non-orientable bipartite graph, we have exactly 7 non-orientable compact tree manifold. So these 7 graphs give, the graphs are different, also the manifold are different, because the boundary is different. In case of orientable up to 8 vertices, there are 6 graphs different, but only 5 orientable compact tree manifolds. So 2 graphs with 8 vertices are non-isomorphic, but give the same tree manifold. So it was the first very naive classification, very naive classification. Then we asked Evgeny, Fominik, and Tarkayev to help us to improve our results, because they live in Chernovitz, they are happy because they are lucky, because there is a very big topological program performed by Sergei school called Recognizer. You give him combinatorial description of the manifold, and the program in many cases gives the topological classification of the manifold. So our first result was that with Evgeny, Fominik, and Tarkayev was that these these 5 orientable compact trimanifold with boundary, non-empty boundary, all of them are exactly complement of knots and links in S3. The 2 with 6 vertices are the complement of the trivial knot, so the manifold was solid torus, and the other was the complement of the op link. And in case of 3 vertices, 8 vertices, there are 3 manifolds, and all of them are complement of links. The first link is not prime, it's the chain with 3 components, open chain with 3 components. But there is also a prime knot with a link with the same complement, the closed chain, because in case of link, there are different links, usually a lot of infinitely many different links with the same complement. In case of knot, it's not true, but for link, it's true. So it's one of the 3 manifold is the complement of the open 3-component chain, but also of the closed 3-component chain, which is prime. And also the other 2 are complement of these 2 links with 4 components. So after this result, we understand that we should proceed our research just focusing on the complement of knots and link in S3. So instead of consider all manifold, bipartite, non-bipartite, and with all type of boundary components, we concentrate our attention in orientable one, and with the boundary which is toric, connected or not usually not connected, because there are a lot of links in this first example. So by using programming model which gives graph, and using also some topological simplification, row pair switching, if a graph contains this configuration, 2 edges of the same color which belong to the same bicolored cycle, 1, 2, and 3. So we proved a theorem that in this case, if you switch the 2 edges, the theorem say that if there are this configuration and at least 2 of the 3 residues involved in this configuration are ordinary, so there is at most 1 which is not a sphere, then the 3 manifold represented by this graph is a connected sum. So there are connected sum of 2 pieces of 2 different manifolds, connected sum with S2 times S1 when all 3 residues are ordinary, and when 2 residues are ordinary and 1 is singular, is the same, some connected sum with S2 times S1 or with D2 times S1. So when there is such type of configuration, the manifold represented is not prime. So in order to generate prime manifold, we can remove all graphs which contain rotary pair of this type. Also, with the rotary pair, instead of 3, there are only 2 colored cycles belong to the same couple of edges. There is some non-minimality condition, so we can remove all graphs containing rotary pair admissible and also rotary pair. So we call this graph without rotary pair and rotary pair, we call them rigid, and we can I will see here. Okay, the second table is interesting. So in terms of increasing number of vertices, 6, 8, 10, 12, 14, 16, the first row gives the total number of graphs without dipole, but including row 3 and row 2 pairs, which are not important. And the third row gives the number of graphs which are rigid, so without rotary pair and row 2 pair. As you can see, when the number of graphs increase, there is a big simplification. For example, with 16 vertices, there are 24,000 graphs, but only 4,000 are rigid. And when the boundary is connected, is the second row and the third row, connected boundary, the simplification is really drastic. 26 graphs, but only 1 rigid, if the boundary is toric and connected. 13 graphs with 14 vertices, no one of them are rigid, and 84 graphs with 16 vertices, only 2 are rigid. So the simplification of rigidity was very important by a combinatorial point of view. So using this concept of rigidity and the program in Modena for generating graph, program in Celia means manipulating and giving the topological properties of the manifold. Also using SNAP-P for the hyperbolic case, we obtain a classification of the manifold up to 12 vertices with non-connected boundary, toric, and up to 16 vertices with connected toric boundary. So this is the result. Up to isomorphism, there are 200 bipartite orientable, so bipartite 4-colored graph without dipole, representing compact 3 manifold with toric boundary, but 106 are rigid, so only 106 should be considered. In the connected case, connected boundary case, up to 16, up to 12 vertices. For connected torids, there are 124 graphs, only 3 rigid, up to 16 vertices. This is in terms of graph, but most interesting in terms of manifold. This is my last result. In terms of manifold, we have the following result. Up to homeomorphism, there exists 24 compact, orientable, prime trimanifold with toric boundary, up to 12 vertices of the graph. And of these 24 orientable prime trimanifold with toric boundary, 22 are complement of links in S3. Only one is a knot, the trivial knot. The other 21 are links. And in case of connected boundary, with connected boundary, there is one up to 12 vertices, the solid torus, and 2 up to 16 vertices. What is the second one? Of course, the complement of the trefoil. So the simplest non-trivial knot in terms of complements is obtained only with 16 vertices. And we obtain before the trefoil knots a lot of links, 22, and we can see them. Okay, this is a 3, I hope it is 3, and then there is, okay, these 2 with 10 vertices, and these 3, 6, 9, 12, 15 with 12 vertices. All of them are linked. This is the name in the Atlas link table. The 4 links without name are not prime, so they are not in the table. Of course, there are some prime representing the same complement, but it's out of the table, too many crossings. Okay, and so we get the first non-trivial knot only with 16 vertices. So a lot of links, but the knot appear only with 16 vertices. There are some algorithms which gives, given a diagram of a knot or link in S3, which give directly the graph, but this algorithm gives graphs which are not minimal, a lot of vertices. So, for example, in case of off-link, in our construction, 6 vertices are enough. In the construction of some French guys recently published, there are 12 vertices, so it's not minimal. Thank you for attention.